so we have the maximum negative moment. We have it to be minus 277.68.69, kilonewton meters. We have the footing itself. If you look at the footing, you are going to see the footing. The point of maximum moment is 2.859 from this end here to this point. We have the point of maximum moment. So let's call that section 1. Now we have from that point of maximum moment, we intend to find out from that point of maximum moment, we intend to find out the width of the footing at this point, which is from here down to here. So let's call from this point down to this point, from here to this point to be K, from here to this point to be K. So we're going to have this. If we have from here to here, and from here to here, we'll add it to the width of this rectangle. So doing similar triangle, we're going to have K to be 1.095. So we'll have 1.095 here, 1.095 here, plus 1.63. So that's what we have here. So the total width at this point of maximum moment is 3.8205 meters. Okay. So having done that, next phase we are going to go into the design proper. From BS8110, we have our K. We'll have it. If we work that out, we'll have the moment. We'll have this. For depth, the effective depth, we're going to have 12.0. Let's assume a diameter of 25 meters. All right. So if we do that, we're going to have that. So if we work that out, we'll have K to be less than 0.156. So we say that the section is okay. Now we look for the lever arm. Work out the lever arm. We're going to have it to be 0.95. Our Z also will solve for our Z. We'll have 0.95 times the effective depth. So area of stay required is this. Work out the area of stay required. We have 8,010 mm square. Now from our reinforcement table, we're going to have the reinforcement for that to be Y40 at 150 millimeters center to center. For as top reinforcement, we have the area of steel provided to be 380. Okay, so having gotten this, we can decide to apply the rules stated by the code. Of course, the code has that rule. Let's look at the rules from the code. Let's look at the rules. All right, so having done that, like we see from the code, we are going to look for the bandwidth. All right, let's check if it is necessary to have a bandwidth for our reinforcement. Now, if we redraw the triangle, we are going to have, let's call the mid part of the triangle. We have LS1, we have LX2. From this point to this point, we call it LY1, and we have the bottom to be LY2. We have the column on this direction. To the column, we have the C2. On this direction, we have it C1. Okay. So now let's check the band if it's necessary to apply the recommendation by the drafting committee of the code. Okay. If it's necessary, we are going to do it. All right. So going by the code, according to what we have, if we have L2Y to be greater than 1.5 CY 2 plus 3D, we'll check if that is greater. If that is greater than 1.5 bracket CY2 plus 3D, we are going to band the reinforcement within this particular band, which is CY2 plus 3D. Okay, but if that is not the case, for the case of this trapezoidal footing, the bandwidth is going to be 1.63. So let's check first whether our L2Y is greater than 1.5 bracket CY2 plus 3D. Now, CY2 plus 3D, remember CY2, Y2 represent the column parallel, the side of the column parallel to the width L2, which is 0.6 mm plus the effective depth 0.934 times 3. So if we work that out, we're going to have 5.103 meters. Okay. Now, if you check the L2, which is the length of the shorter side of the trapezoidal footing, 1.63 meters, you see that it is not greater than 5.103 meters. So if that is the case, since it's not greater than that, bandwidth of CY2 plus 3D equal to 3.4 will not be applied. So we're not going to apply this length as the bandwidth. So what we are going to do, we're going to take um, we're going to make use of LY2. We say, but LY2 becomes 1.63. So the bandwidth we are going to take in this case will remain within LY2. All right. Unlike the case we have for other footing, but in trapezoidal footing, since this is not greater than this, you assume the bandwidth to be LY2. So we are taking LY2 as our bandwidth. And the recommendation is that 2/3 of the reinforcement should concentrate within that bandwidth, which is 1.63. All right, so let's look for 2/3 of the reinforcement. We'll look for that. 2/3 of the reinforcement will give us a 5,340 mm square. Okay, so that is 2/3 of the reinforcement. So we are providing a Y12 at 32 at Y32 at 125 millimeter center to center as the top reinforcement within this band. Now, within the band of 1.3, that's where we're going to have it. Now, the remaining parts of the footing which are not lying within the band will share the remaining reinforcement. So if we have this as a reinforcement, the remaining reinforcement will be shared between the two other sides, which is from this portion and this portion. So if we do that, we'll have both portion to be having Y25 at 300 millimeter center to center top. Area of C provided is 1640 millimeter on both ends of the band. Okay, so let's look at the detailing and let's see how the detailing is going to go. Let's look at the detailing. So if you look at the detailing, you're going to see at this point, Y12 is lying, Y25 at 300 millimeter center is between this point down to this point, which is outside the bandwidth of 1.63. From this point to this point, we also have the same reinforcement, Y25 at 300 center to center top. And within the bandwidth, which is this portion with dotted lines, these portions with dotted line will have the bandwidth, which is 1.63. We'll have the reinforcement at this point we'll have the top reinforcement at this point to be Y32, Y32 at 125 center to center top as the main reinforcement. Now, the next stage, we are going to look for the distribution bar, both for the top and for the bottom reinforcement. All right, so we want to obtain the distribution bar. Now, for distribution bar, we said the minimum reinforcement according to our code is 0.13% of the cross-sectional area. And if we do that, we're going to have 1,300 mm square per meter. Remember, we're using, in this case, we're using 1 meter width slab. All right. Now, area of steel provided is 1,640 by 25 at 300 center to center, top bottom. All right. So we have this as our distribution bar. Now, this distribution bar, we're going to use it for both top and bottom reinforcement. Okay. Now, let's look at the main reinforcement, our bandwidth. We already have our bandwidth to be within this point. So we'll have it as a 12Y32 at 125 center to center, top reinforcement. All right. So that is what we have for this particular one. And we have the bandwidth already as 1.63 meters. Now, the method of detailing differs. This is just one method. The other method is to have the longitudinal bar parallel to the parallel side of the trapezium. We can have it that way. If we do that, we can have the longitudinal bar parallel to the parallel side of the trapezium. Then we'll space it as that. Okay, so now this other way, this is the other area where we have 2/3. The 2/3 is the bandwidth. The remaining portion will have Y25 at 300 center top. Similarly, we have the same for the other side, which is Y25 at 300 millimeter center to center top. Okay, now we have also the bar, which represents our bottom bar. our bottom bar, which is going to act as distribution bar for bottom. You can see it here. We'll have it as a Y25 at 300 millimeters center to center bottom. Okay, so this is just one of the methods we can detail. Now for bottom reinforcement, I need to show you how we arrive at the reinforcement for bottom reinforcement. Uh, we arrive at the bottom reinforcement. Now, for you to design the bottom reinforcement, you need to divide the trapezium into two equal parts. The span of the trapezium is divided into two equal parts. So we have 2.6625, 2.6625. So now, having done that, the next thing you are going to do is to take each part that is attached to the column as a isolated part footing. All right. So if we take this particular portion as an isolated part footing, we are going to look for the moment of the pressure about the surface of the column, especially this column. So in this case, we are not going to treat the column at our left-hand side. We are going to deal with this at our right-hand side. So the whole pressure acting on this place, we know it to be 255.34 kilonewton per meter square. So this pressure will act on this surface. So we'll look for the moment it's going to produce about the surface edge of this particular column. All right. Now, for us to do that, we need to multiply the area of the pressure times the area of this region shaded times the centroidal distance to the surface of the column. But in doing that, I'm going to discretize that portion into two parts. These other parts that represent a triangle, these other parts represent a square. So the pressure will act on this part and will also act on this part. So we'll calculate the moment of that pressure about the surface of this place when it acts on this rectangle plus when it acts on this triangle. So the two portions. So I'm calling the portion for easy understanding. Let me label it for your understanding. We can call here 1. We can call this point 2. We can call here 3. We can call here 4. We can call this point 5. So the triangle I'm going to concentrate on is this. So remember, from here to here is 5.325. Also remember that from here down to here, which is this particular portion, is 2.04. The total length or the width of this portion is 7.1. So here also is 2.04. So the bandwidth, which is 1.63. So if you add them up, you have the total length at this direction to be 5.71. Okay. So for clarity, we are going to isolate this part of it so that we'll see how we can obtain this point from here to here, because the pressure at this point is going to act at the center of this triangle down to this point. So we'll add it. Let's call that triangle from here down to this point Y. Okay. So we have 2, 3, 4. Let's call it Y. 2, 3, 4, 1, and 5. All right, so let's draw them out so that we can have understanding of how it is arranged. Okay. All right, so if we arrange the triangle like we did, this is 1, 2, 3, 4, 5. So if we turn it upside down, our Y remain what it is. We look for the Y. If we look for our Y, we are going to have our Y by similar triangle. We are going to have our Y to be this 1.02. So if we have 1.02 for our Y, we can now say the moment of the pressure about the face of the column at the right hand side. We call it, this becomes the pressure times the area. It becomes the pressure times the area. Okay, so the pressure times the area times the centroidal distance to the surface of the column will give you this. That is, we have this. All right, now we have the pressure from that of the triangle. We have two portions now. We have portion A. Let's call this one A1. Let's call this one A2. So the load will act at this center here for portion A, while the load for portion B will act at this center. So if you work them out, and the pressure is 255.34 0.34. So if you work that out, acting at this point about this surface here, this one acting at this center about this surface here, they are going to have the moment, the final moment will be 80166.650.71. If we do that, we're going to have the total moment to be 1,452.39 kilonewton meters. Okay, so having gotten the moment at this stage, we'll know what our effective depth is. We'll work that out. We can now calculate the area of the footing, especially the bottom reinforcement of this footing. So whatever we obtain for that particular footing will also be used for the other one. All right, so we'll go ahead to do that. All right, so having gotten the moment, let's calculate the area of the section. We have our LA Z to be 0.95937.5. The area of steel required is 1,450 divided by 0.95410, which is the strength of steel. And we'll have the area required to be 4,186.9 mm square. Okay, so I haven't gotten the area of steel required. We can convert that area to area per meter square, of course, per meter width of the slab. All right, so we know that the width at that point is 2.6. Remember, we are looking at it from this direction. So we're looking at it from this direction. So it's going to be, the reinforcement is running this way. So we are going to be looking at it in this direction. So we'll divide it by the length, which is this particular LX2. Okay, so if we do that, we'll have it to be 1,572.5 mm square as that particular area of steel required. All right, so based on the fact that we've done this, from our table, which we are using to check area of steel, is calculated per meter width of a slab. So that's why we are dividing by 2.6625. All right. So since from that table, if you check the table where we have area of steel per meter width, you discover that we'll have that area to be Y20 at 175 millimeters center to center. And remember that it's going to be a bottom reinforcement. So it's going to be at the very bottom of the footing. Okay. All right. So before we go into the final details, of course, like we've done in before now, we will check if the reinforcement will be bounded for the transverse direction. Remember that the reinforcement is moving in this direction, it's spanning in this direction, so we are likely to bound it between this LX1 width. We need to check if it will be bounded between the LS1 width, or we just need to distribute it evenly. Okay, so but for us to do that, remember what we said, that LX1, which is this is our LS. The code says that for us to bound it, we must check if LS1 is greater than 1.5 as 0x, CX1 plus 3D, where CX1 represents the column, this particular length of the column. Of course, we have that to be 600. So if we do that, we'll have the value as shown. So our LX1, we can see that it is not greater than this, so it's not true. So since it's not greater than 51187 meter, we'll have it to be 2.6625, so it's not greater than that value. So what it means is that we cannot bring in bandwidth into this detailing, okay? So now we are not bringing bandwidth. What it means is that our area of steel provided should be evenly distributed within these points, okay? But if we do that, for us not to work on this other part of the footing, remember we said we'll divide the footing into two equal isolated footing. We'll make use of the reinforcement obtained for this particular section of the footing for this section on the left hand side, which is our LX2. So this same reinforcement obtained will be used evenly distributed along the span. All right, so that is what we're going to do. So we say area of steel provided is 1,800 mm square, evenly distributed for span LX2. We also use the same reinforcement. Okay, so this is what we have for this particular footing. So the bottom reinforcement in the transverse direction has been obtained. Um, so we can do a complete detail of this particular footing. The first one we didn't incorporate the reinforcement at the bottom part of the plan, but now you can do a complete detail that will incorporate the bottom reinforcement, and we're going to cut a section across section AA so that we can see clearly what is happening at this section. Okay, so we are done with the design of this design for bending moment. The next thing we would like to do is to check the shear capacity of the section, and we check the shear capacity, and we also check for the punching shear capacity. Of course, the shear capacity, is a one-way shear check, while the punching is a two-way shear check. So we'll do that also. Let's go over to that. All right, so now let's look at calculating the shear capacity of the footing. Now we can see that from the point of zero shear force, from the very end of the footing, that is from this end. So from this end to the point of zero shear force, we'll have the value to be 2.859. This is the point of zero shear force. So we are going to calculate the shear force from the face of the column. Now from the face of the column, we are going to take half the span of the shear span. So from here down to this point represent the shear span. So half of each, if we take half of this shear span, remember, we are going to take it from the face of this column. All right, the face of this particular column. So if we do that, we have knowing fully well that this column is 2.859. We'll have that as the shear span of this column. So, but we're going to pick it from the face of the column. Then we're going to take half of the shear span of the column. So we're going to design the shear force, making use of the half of the shear span of the column. So if we do that carefully, we are going to have the shear span to be equal to 2.859 minus 0.45, which is the width of this column on this direction. So if we do that, we'll have it to be 2.409. So we'll have it to be 2.409 as that particular span. Okay, so having done that, we would like to look at the weight of the base is known. We've done that before in our work. We've done that. We know that the width at the point of zero shear force is this point, and it is 1.0 meter from here down to here. So we know that. So the next is for us to have the shear force that represents half of the shear span, is for us to go back to our shear force expression. From the shear force expression, we can carefully obtain that particular value for shear force that represent the distance from the face of the column, that is 1.2045. Okay, all right. So but if we're taking it from the face of the column, we add this to it. So that distance, because that distance becomes 1.654. We'll have it here, 1.654 meters from the zero end of the footing down to where we have half of the span, the shear span. Okay, so having done that, we'll look for the value. The value for shear force at that point is negative 1033.6 kilonewtons. We'll have that as the value for the shear force. So if we have that, we can as well obtain the shear stress at that point. Now, if we work at the shear stress at that point, we'll have it to be Um, we have the width, and we divide by the effective depth of 937.5, and we'll have that to be 1.0068 Newton millimeter square. All right, so we have that the shear stress. Uh, Now we need to look for the value for shear from our code, BS 8110. You can check that out for an effective depth of 93 from table 3.8 of BS 8110 1997, part 1. So you can check that out and obtain that value for the shear. All right. So having done this, we'll go into the check for the punching shear. But before we do that of the punching shear, it is necessary we equally check this other side of the footing. Remember that from the face of the footing, we are taking half. So we can check that expression and obtain the shear value for from this point here to half of the shear span on this direction. All right. So if you are doing this design, you must check for both sides. I may not be doing that in this particular problem, but I want you to do that on your own. You check using the shear force expression. Check from the face of this side of the column uh, down to half of the shear span, and check the shear stress at that point to be sure that it complies with the maximum shear stress as given by the code. All right. But if you work this out, you observe that whatever value you have, whether it's greater than 1033 or whatever, you discover that the shear capacity of the section is still okay. All right. So, but let me just stop by checking that of this point down to here. Maybe what we want to you can check from this point down to here. Remember that the total length. All right, so we know that the total length of the footing is 5.325 meters. And if the point of zero shear force is this point, we can as well calculate the value for the remaining part of the column of the footing. So all we need to do is to subtract 5.32 from 2.859. All right, so we are going to look at the shear stress. So working out the shear stress from the code, the formula will have it VC 0.79. We'll have that formula for shear stress. So we can obtain that from BS 8110 table 38. We can get the notes from table 38. Of course, follow it. We have 400 over 937.5 raised to the power 1 over 4. And that value should be greater than 0.67 for slabs. All right, so we equally have our FCU to be greater than 25. Of course, as stated by the code, when FCU is greater than 25, the value should be multiplied by FCU over 25 raised to the power 1 over 3. All right, so that's exactly what we've done. So our BC, our shear force is equal to 1.0625 times 0.52639. Okay, so if we work that out carefully, we're going to have the shear stress to be 0.559 Newton per millimeter square. All right, so you can see that the section has satisfied the shear requirement, so the section is okay since it is lesser than 0.8 the root of FCU. So we'll find out that the section is okay in terms of shear. Now, another check we're going to check is punching shear. Of course, BS 8110 for punching shear will have the distance of the face of the column to the critical perimeter to be 1.5D. CP115 gave a more accurate value, 1.5H. Of course, we know that the shapes are different for each of the code, but CP114 appears to be more accurate, though a little bit complex in determining the area of covered by the punching shear. So we're going to work with BS 8110 1.5D. We have that to be 1406.25 mm. That is a critical perimeter from the face of the column. Now, if you look at the critical perimeter, you will observe that indeed it is more safer to make use of the critical perimeter within the perimeters of the column. All right. Of course, you can see that the edge of the column, at the edge, there's no extent continuity of the slab at that edge. So if we don't have a continuity of the slab at this edge, this is the edge. All right. So if there's no continuity to the left, to the right hand side, the reality is that we are likely to express punching in that direction. So the critical perimeter most likely is on this part of the column. These are more critical because there's a high tendency for this column to punch away from the entire footing. Okay, so because of that, it is advised to take the critical perimeter as the perimeter of the column itself. Okay, so but if we want to do the critical perimeter at 1.5D, you see that the total perimeter from here to here is 1.5D, which represents 1,400. So if we do add it up to 600, we'll have a 2,000, and then you work out the rest. Okay, so the total perimeter from here down to here will give us 5,418.75 mm. But we're not going to work with that critical perimeter because it is not as critical in terms of punching. The most critical perimeter for punching in this problem is the perimeter at the extreme end of the column. All right, so because of that, we're going to make use of the perimeter of the column as the critical perimeter for punching shear check. Okay, so we have the load acting on that critical perimeter to be 3,000, which is the ultimate load of the column B. So if we have that, the perimeter is 600 plus 600 plus 600, which is 1,800 mm, times the effective depth of the footing, which is 937.5. So if we work that out, we're going to have a 1.77 Newton per millimeter square, which is equally less than the maximum shear required for the section. Okay, so we can confidently say that the section will automatically satisfy punching shear requirement. All right, so this brings us to the end of this lecture. If you find the lecture helpful, do well to hit the like button as well as subscribe to the channel. I'll see you in our next class. Have a wonderful day.